Now it is your turn. Let's build and measure this chapter's sorts and searches in C. For Lab 1, your job is to implement 3 sorts and confirm they agree. The first is insertion sort, taking the array A and its size n. The second is merge sort, with the same signature. The third is quicksort. It wraps a recursive helper over the range low to high. Test all 3 on the same 9 values, 9, 3, 7, 1, 8, 2, 5, 4, 6. Every result must come out sorted, 1 through 9, no matter which sort produced it. One tip: merge sort needs one malloc auxiliary array freed before it returns. Quicksort needs a partition helper. Insertion sort needs neither. Take a few minutes and try it yourself before you look at the solution. Here is one clean solution, starting with insertion sort. Each pass saves A at I as the key. Then shifts every larger element in the sorted prefix one place right until it finds the key spot, and drops the key in. That is the whole algorithm. Now merge sort. The public function takes the array and its size. It allocates the auxiliary array once here at the top level. Note it is not allocated inside the recursion, which would be 1 malloc per call. It hands the work to the recursive helper, and then frees the auxiliary array, 1 malloc, 1 free. And quicksort's public function has the same shape. A base case for 0 or 1 element, and then a call into the recursive helper over the closed range low to high. Notice all 3 public functions take the same array and size arguments, only the machinery inside differs. And here is the point of running all 3. They agree. All 3 reach the same sorted array from the same starting shuffle. The answer never depends on which sort you pick, only the cost does. For Lab 2, instrument insertion sort so it counts its work. Every comparison it makes increases a comparison counter, and every move increases a swap counter. Do the same for quicksort's recursive helper over the range low to high. Then run each sort on 3 inputs, all built from the same 8 values, an already sorted array, a reverse sorted array, and a random order array. Before you run it, make a prediction. Which sort do you expect to do less work on already sorted input? Which one does the same work no matter the order? Think about it, then run it and check your guess. Let's look at the solution. 3 global counters hold the totals, comparisons, swaps, and shifts. Insertion sort shifts, quicksort swaps. They are counted separately on purpose. Each time through the inner loop, we increase the comparison counter by 1, because we are about to compare 2 elements. If the element on the left is already less than or equal to key, we stop. The prefix is sorted, so no more work is needed here. Otherwise, we shift the bigger element 1 step to the right and increase the shift counter. Note it is a shift, not a swap. 1 assignment, not a pair exchanged. When the loop ends, we drop key into its gap. Here are the measured counts. Insertion sort on sorted input makes only 7 comparisons, which is n-1, and 0 shifts. That is its best case, and you can see the adaptivity as a number. On reverse input, the same algorithm makes 28 comparisons and 28 shifts, its worst case. Now quicksort on that same sorted input, 28 comparisons, which is 8 times 7 over 2. Its worst case, on the input that was insertion sort's best. And quicksort on random input, only 14 comparisons. So the 2 algorithms respond to input order in opposite directions. One more note on the columns. Insertion shifts one element per step, while quicksort swaps a pair, so those two columns are not counting the same operation. For Lab 3, the challenge, write linear search that counts its probes. It reports each probe through a probe's pointer that the caller passes in. Then write binary search that counts its probes too. Binary search only works when the array A is already sorted. Run both on the same set of keys, including one key that is absent, and compare the probe counts. Predict first. For m equal to 12, binary search's worst case is about log base 2 of 12, which is around 4 probes. And which key forces linear search to its worst case? Try it before you check the solution. Here is linear search, instrumented to count probes. It takes an extra pointer probes that it increases as it goes. The loop locks every index. And this is the instrumentation. We count one probe per element examined. Note it is counted before the comparison, so a probe means a slot we had to look at. On a match, return the index. And otherwise -1. Everything else is unchanged from the plain version. And here is binary search with the same instrumentation. Low and high bracket the interval. Each round computes the midpoint and counts one probe. So a probe here means one midpoint examined, which is exactly comparable to linear search's one slot examined. On a match, we return the index. And otherwise, we have the interval and go round again. Now the numbers. For key 5 near the front, linear search takes 3 probes and binary search takes 2. On a lucky key, linear search is competitive. For key 56 near the back, linear takes 10 probes and binary takes 4. The gap has opened up. And for key 100, which is absent, linear search hits its worst case. All 12 probes because it has to check everything before it can say no. Binary search stays at 4, which is close to log base 2 of 12. So here is the closing thought for the whole chapter. Sorting once costs big O of n log n. It pays for itself as soon as the structure is searched more than a few times. Sorting is an investment, and every search afterwards is the return. That is exactly the sorted phone book we opened with. Nice work getting through sorting and searching.